Okay, so we have a quiz today on two sections, section 2.1 and 2.2. So the first thing I like to do is just answer any questions you have about problems from that section. So we'll start with 2.1. Any questions on 2.1? This was the distance formula section with the midpoint formula, determining types of triangles. Any questions on 2.1? Yes, sir.
For the quiz, do we need to know the distance formula and the midpoint formula?
I give you those on the quiz.
Okay.
Yeah, so you don't have to memorize those. So you just have to know how to use the distance formula for a triangle, most likely. Anything else in 2.1? We're good on 2.1. All right, how about 2.2? 2.2 was on creating graphs, if my notebook will let me go to it. Creating graphs if you're given x coordinates, right? So you have to calculate the y coordinates and then make the graph, figuring out intercepts, and then testing for symmetry. So would anyone like me to go over any homework problem? Yes, sir. 61 in section 2.2. So this is 61. So this is finding the x and y intercepts, if any. Okay, so we have the equation y equals the square root of 9 minus x squared. Okay, so x and y intercepts. For the x-intercept, what you're going to be doing in this equation you're given is you're going to be substituting 0 for y and then solving for x. So let's see what we get here. So we're going to plug in a 0. So we have 0 equals the square root of 9 minus x squared. All right, so we have to solve this equation. So if you think back, to solve this thing, you have to square both sides to get rid of the radical. So we square both sides, the 0 doesn't change, and you get 9 minus x squared. And then we'll solve this for x. I'm going to move the negative x to the other side. So we're going to get x equals plus or minus 3. Okay. All right, so the only thing is when you square things, you have to make sure you get a corresponding y coordinate. Okay, so you have two x possibilities here for the x-intercept. You just have to make sure that when you actually plug those numbers into the actual equation, you're going to get real y values. And clearly you will here, right? If you plug in a positive 3 for x squared, you'll get 9 minus 9, so y is 0. And then if you plug in negative 3, again, you're squaring something that's negative. It becomes positive. It's still 9 minus 9 is 0. So these are both x-intercepts, so they'll be located at negative 3, 0, and 3, 0. So they're your two x-intercepts. Now, depending on the equation you're given, you might not always have two, right? If you remember from section 2.3 on lines, you might only have one intercept, okay? So it just depends on the specific equation. Now, for y-intercept, you don't plug in y is 0. You're going to substitute 0 for x and then solve for y. So let's see what we get. So we have y equals the square root of 9 minus 0 squared. So that's just y equals the square root of 9. So that's y equals 3. So it only has one y-intercept, and it's at 0, 3. Square root of 3? Yeah, it might have just been a typo. Yeah, but this is it. Because, I mean, if you were to plot this thing, this basically is a semicircle, right? So, I mean, it's definitely going to have two x-intercepts and then one y-intercept. But, yeah, I don't think it's the square root of 3. Now, it's all three, whole numbers here. Okay. Yes? 51. Sure. So 51 is another x-intercept. So here we have 3x plus 4y equals 12. So we're going to do the same thing, right? We did in the previous one. We're going to find the x-intercept. Plugging in y is 0. So you have 3x plus 4 times 0 equals 12. So that's 3x equals 12. And then x equals 4. So we're only going to have one x-intercept at 4, 0. And if you're thinking about section 2.3 from Tuesday, if you were to graph 3x plus 4y equals 12, that's going to be a line, right? So we're only looking for one intercept in the x and maybe one intercept in the y. So let's see what happens. We're going to plug in x is 0. So the first term goes away. We have 4y equals 12. So solving for y, you get 3. So that means we're going to have a y-intercept at 0, comma 3. All right, so there's an equation. When graphed, we'll only have one x-intercept and one y-intercept. Okay? Anything else? Any symmetry problems you like? Yes. Sorry, I couldn't see your hands. I want to go first, Pat, and then Lauren.
Can you do 69?
Sure. All right, so 69, we have, here's the equation, y equals 5x to the fourth plus 2x squared. And we want to determine if it has any of the three symmetries discussed in section 2.2. So we have to test for all three. So we have x-axis symmetry. So this is easy to remember because if you think about x-intercepts, we were doing something with the y variable, right? With x-intercepts, we subbed in 0 for y. For x-axis symmetry, we're going to sub in not 0 for y, we're going to sub in negative y. All right, so every time you're talking about the x-axis, you're doing something with y, and then with y-axis, you're doing something with x. So here's the easiest way, I think, to do these problems. You just change the y part of this equation, so in this case, negative y, and then leave the right side the same because you're not changing the x's here. And then what you have to do is just isolate y again, which means we have to make y positive. So what's the easiest way to make a negative y positive? Wouldn't it be just multiplying everything by negative 1? Right, that'll make y positive again. But we have to multiply everything in the equation by negative 1. So by doing that, all we get is y equals negative 5x to the fourth minus 2x squared. So for x-axis symmetry, all you have to do is whatever you get once you isolate y, if it's different from what was on the other side of the equation from y initially, if they're different, you do not have that type of symmetry. All right? If they happen to be the same thing, then you do have that type of symmetry. Okay? So for this one, they're different, right? Because I have negative signs. So that means, no, we don't have x-axis. Now for y-axis, we're going to substitute negative x in for all of the x's we see. So this is what this will look like. Y equals 5 times. So now instead of having x to the fourth, we're going to do negative x to the fourth plus 2 times negative x squared. All right? So now for y-axis symmetry, you're not going to multiply by negative 1. You just simplify the right side of the equation. Okay. Well, what happens when you square a negative number, right? It becomes positive, right? So if you square a negative variable, the variable becomes positive. And really, if you raise any negative variable or number to an even exponent, you always end up getting a positive result. So this right side of this equation will result in 5x to the fourth with no negative sign plus 2x squared because all those exponents are positive. So now, is that the same thing from what we started? It is. So we would say, yes, you have y-axis symmetry. The last type is origin symmetry, and you do both. You sub in negative x and negative y and go through pretty much both of these processes to get to that last point where y equals something and then check it from the original. So we have negative y equals 5 times negative x to the fourth plus 2 times negative x squared. Now what's nice is we already know what this results in. It results in 5x to the fourth plus 2x squared. And then all I got to do is multiply everything by negative 1 to get y isolated and it to be positive. So we have negative 5x to the fourth minus 2x squared. So that is not the same. So no, we don't have origin symmetry. Okay? So the result here is, yes, we have y-axis symmetry. Are there equations out there when graphed that don't have any symmetry? Yes. So you could get no, no, no. You could get yes, 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 and then you can get some other combinations just depending on the equation. Okay? Lauren, what was your question? How about that? There you go. But that was a good review for symmetry. That's what you do. You just test for all three, and your answers are no, yes, or no, or you're just a series of, or the subset of no's and yeses. All right, anything else from 2-2? Okay, seeing no hands, that is, we'll wrap those two sections up then today with that quiz. Okay, and we'll do that at the end. All right, so there's the review for the quiz. So section 2.3, which was from the video that was posted Tuesday, we're on graphing lines and then writing out the equation of lines. So this was the homework assignment in 2.3. Are there any questions about the 2.3 homework assignment? At some point in your lives, you've definitely graphed lines and wrote equations of lines, so I'm hoping it was somewhat of a review. Anything else? Anything I could go over about lines? All right, really, the only thing I might mention, just to maybe force a little review on you because I wasn't here. Let's see, where did we start? So we know about how to calculate the slope of a line, right? Rise over run, that's easy to remember. Rise is the y direction, run is the x direction. And your slope can be rising, which means the slope is positive. The slope could be negative, which means it's falling. But then there were two special cases, right? If you had a vertical line, which has an undefined slope, or a horizontal line that has zero slope. And you could use the slope and the y-intercept to actually write out the equation, right? So I'm just going to box this thing here, right here. We looked at an equation like that. That was number, 51 in the previous section that we went over about finding y-intercepts. So you'll see what happened. What did we do? We just solved that equation for y, and it ends up being in slope-intercept form, right? We solved it and got y equals 5/7 x minus 5. So we know the 5/7 is our slope, and we know -5 is the y-intercept, so that's 0,5. So we have a point to start with, and then I actually went ahead and solved for the x-intercept by plugging in y right here, and I got 7, 0, and then you're able to plot a line so long as you have 2 points. So if you can get the 2 intercepts, there's your 2 points, because they're probably the easiest things to calculate. And then you just draw a straight line through those 2 points, okay? Easiest way to do it. Then we ended up using this equation here. This was point-slope form to actually actually write out the equation of a line. All right, so if you're given the slope and a point, you literally just plug the numbers in and then, again, solve for y. Another example, and again, it depends on what you're given in a problem. So your goal is to always at least have 1 point and have the slope. That's the point of point-slope form. So the equation name is telling you the 2 things you need in order to write the equation out. So in the second example here, I gave you 2 points. Well, if you have 2 points, that means you can find the slope. So you find the slope, and then you can choose any of those points to write the equation out. And then the last thing in this section was parallel and perpendicular lines. So if 2 lines are parallel, they have the same slope. And if they're perpendicular, the slope looks like this. It'll be the negative of 1 over the slope of the other line, which means they're perpendicular. And that pretty much wrapped up that section. So are you sure there's no other questions on that homework? We're okay? All right, perfect. All right, so we'll move right along. Now we're going to do section 2.4. And if I usually look at the clock on quiz days to make sure, but if we get to the point where we're around 9:20, raise your hand and say, hey, we're getting close, could we start the quiz? That's completely fine. Some of these chapter 2 sections are rather short. And this one is one of those sections. So section 2.4 is on functions. So during previous classes, you may have heard me say functions on accident. I was trying only to say equations, but really the equations we were working with are also actually mostly functions. So if you heard me say functions before, that was why. So here's an equation we've worked with, or at least the structure of this type of equation we've worked with. We had like y equals 5x minus 2, right? We all know what that is. So it's a line. We know the y-intercept is 0, negative 2, and we know the slope is 5, okay? So I'm just going to rewrite it as a function, and you're going to see that really, it's really not that much different. So instead of having y, okay, we're going to rewrite this as f, and then in parentheses put an x, okay? Now this is how we say this. We say this as f of x. And it means it's a function with x as the input variable. All right, so what the heck am I talking about? So y'all have a calculator. You've used a calculator before, right? Every time you hit one of the buttons on your calculator, you're using a function. And that function requires something, right? If you wanted to do, let's say, the square root function on your calculator, you hit the square root button, right? And then you have to give it a number, right? That number is the input to the square root function, right? So all I would define x as in this function, I like to call it the input, all right? But it's also termed the independent variable, okay? Independent variable. All right, so f of x, the left side of the equation is that. The right side, this 5x minus 2, that actually doesn't change. So the only thing we're changing here is we're going from a y to f of x. All right, so functions like that square root button on your calculator, when you put the square root of 16 and hit enter, right, you get a result. You get square root of 16, you're going to get a 4 on your calculator. So that would be this part here, all right, when it's evaluated is the output. Right? Remember, functions has to have an input, has to have an output. And we call that result is the dependent variable. Okay? So why is it dependent versus independent? Well, it's dependent on the x term, right? We can't have the output to the function without an x term, right? So it's dependent on that independent variable, which the independent variable isn't dependent on anything. Does that make sense? Like you can't get 4 without actually first plugging in 16 into the square root function. So far, so good? All right, so this will actually help us better plot equations because really, you can really make any equation into a function by doing this. Let's say we wanted to figure out, well, what's the coordinate on a plot for this function where x equals 4? All right. We would say, well, it's not f of x anymore, it's f of 4 equals 5 times 4 minus 2. So that means f of 4 equals 20 minus 2, which is 18. So we can get a coordinate when we actually put a number as the input and then get a result, which is also a number. We get an ordered pair, which is just a point. We get the point 4, 18. So by plugging x values in, you can get points. And then you can just put those points in on the graph. And that's kind of why in section 2.2, you were given that table graphing homework problems, right? You're given all the x values, again, independent. You can choose whatever they are. And then the y value was the dependent variable, the output to the function. Okay? Now, just like equations have a domain, so do functions. So I'm going to give you the mathematical definition of domain. Okay. Now you already know how to do this. It's just going to be using this terminology with functions, because that's really what we're doing with equations. So the domain are all values all values of the independent variable, so x, or whatever variable you use, it doesn't have to be x, all values of the independent variable to a function that results in a real number. Okay? So all values of the independent variable, so this is x, that when plugged into that function give you a real number. So the domain here in our example, so I'll put this here for the example above. If I plugged in any x value, right, it's a line. If you remember anything from the line section, you know that you could go all the way to the infinity, right, in the y direction, or in the x direction, and all the way to infinity in the other positive x direction, and you'll have real results. So we're going to go ahead and describe the domain of the function. I'll even put the f of x here so you realize to go back to it if you're looking at the notes. And you put it in, you use interval notation. So if the domain is, I could plug in any x value, the domain is always negative infinity to positive infinity. It just means you can plug in any real number. That's what that means. So again, the domain is always looking at what we would plot on the horizontal axis. And just, I guess it's just from common use over the years, x seems to always be that horizontal variable. It could be any other variable, but we use x a lot. So try to just think of x as horizontal for now at least. All right, so that's domain. Now there's another description for a function that I don't think we've talked about yet. It's called range. There's domain and range. So this is the set of all outputs of a function based on the domain. Okay, I'm going to put something in parentheses here by outputs. So set of all, maybe I'll even put a caret here. Now, if you have an output to a function, it has to be by definition real, but just so you have that there. So it's set of all real outputs of a function based on the domain. Now, this one's trickier to figure out for certain functions. Now, for a line, let's see. So for this f of x, right, we're going to have what's the range? What do you think? What's the range? So this is going to be the set of all real outputs for a line. Now, I'll actually even go ahead and graph this. Well, we know the y-intercept is at -2, and the rise is 5 over 1. So I'm going to go up 5 and to the right 1 because the slope is positive. So 1, 2, 3, 4, 5, 1. All right. So when you draw the line, you're looking in the vertical range to look at the range. So how would you define the range of a line? So this is all the real outputs of a line. What do you think? What would it be? So doesn't it look like I go all the way to positive infinity and then all the way to negative infinity in the y direction, right? Does everyone kind of see how that works? If that's the case, then your range is also negative infinity to positive infinity. Okay? Okay. Now the range algebraically can be difficult to calculate, but if you have the graph of the function, if you have it plotted, the range and really the domain are also very easy to find. Okay, so here's what I'm going to do. Let's just start with some equations and see if we can figure out the domain and range. Let's see if it's easy. It may not be. All right, so we did that line. Okay, so this is a good one. What if I did I'm going to switch it up and stop using f. You could use anything. The variable doesn't have to be f. So I'm going to use h of x. So this is a function h with a single input x. And I'm going to write it as the square root of x plus 3. Okay? And all I want is, right now we'll just talk about the domain. Okay? All right, so how do you find the domain? What did you do? Well, for this one, right, since we have a square root, what do we have to worry about popping up if we plug in certain f values? Is it possible to have an imaginary output to this function? Like, what if I plugged in negative 4? What would I get on the right-hand side? Like, if I did h of negative 4, I'd get the square root of negative 4 plus 3. I'd get the square root of negative 1. Oh, so I get I. That's imaginary. When we're talking domain and range, we can't have imaginary outputs to the function. So what that says is the range is not, or the domain is not going to be negative infinity to positive infinity. So when square roots, remember, this is what we did. We took the radicand, the thing inside the radical, x plus 3, and we said, okay, well, that has to be greater than equal to 0. Has to be. Otherwise, we're going to get an imaginary solution. So then we solved this and saw that x is greater than equal to negative 3. Well, that's going to be our domain. We just have to write it in interval notation. So what's x is greater than equal to negative 3 in interval notation? What would it be? Yeah, go ahead. What do I put on the ends, though? Yeah, I got a bracket here, and then infinities always get that. So there's my domain. Okay? Well, when you look at that equation, it's a little bit more difficult to figure out the range. But if you had the graph of it, and I'll just give you the graph of it. And again, this is just a sketch. Now I can find the y-intercept here. I'm sorry, the x-intercept would be if I plugged in, so x-intercept, I'm plugging in y as 0, right? So basically I'll have 0 equals the square root of x plus 3. If I square both sides, it's essentially going to end up being negative 3, 0. Like if you plug in negative 3, you get the output to be 0. So here's negative 3, 0. And without plotting any more points, it essentially has this shape. All right? So it looks like that matches the domain, right? So if you had the plot to begin with the domain, you could just say, well, yeah, it's got to be negative 3 up to positive infinity because I have a solid circle here. If I had an open circle there, what would that mean? It does not include that value, right? But solid means we keep it. So range here, somebody take a stab at it. What's going to be the range of this? So again, it's all the y values from the plot. And again, that really is all of the outputs to the function. What would it be? What's the smallest y value on this graph? Yeah. That's an x value. What about y? Well, okay, what's the y value at that location? Okay, 0. So that's the lowest, right? And would I have a square bracket or a parenthesis? Yeah, because it's a solid circle, right? So square bracket 0. And where does it look like that function is going? It looks like it's just growing and growing and growing. So isn't that going towards positive infinity? So it's 0, comma, positive infinity. That's the range. So if you have the graph, it becomes fairly simple. All right. Now some of the questions in this section, they're going to give you graphs. Okay. So let's go ahead and just do a couple of those examples since I started that here. But that's essentially what, I mean, to be honest, every problem in this section is determining domains and ranges of functions. We kind of have to have that down to continue on with, because the next couple sections are going to be about functions. All right, so here are some graphs, and we'll just go through them. So here are some examples. So give me a second to get some of them here. and I'll try to draw them as best I can. Also, if we have functions, instead of labeling y on the vertical axis, you'll put f of x, or whatever the definition is there. So let's say we had something like this. So I'm going to have okay, so I would like the domain and the range based upon that plot. Somebody help me out. Yeah. Up here, that's a hollow circle. Yeah. So remember, solid circle means it's in the graph. Open circle means it's not there. So what about domain? So what x values are represented in this graph? So we have the tick marks are 1, 2, 3, 4, right? So somebody give me the interval. Yeah. So a closed bracket on 1. I agree there. But you see that, so for infinity, I'd have to have like an arrow at the end, meaning it goes on forever. Now, is it a bracket or is it a parenthesis? It's a parenthesis, right? Because I'm not including 4 because I have that open circle. Now, how about the range? Again, so this is 1, 2, 3, 4. Well, it looks like my lowest y value is 1, and I have a closed circle. And again, it goes up to 4, but it's an open circle. So the domain and range are the same, and that's possible. Right? We saw that for a line, the domain was and the range are identical with that negative infinity to positive infinity. All right, so that's a simple example. How about this one? Some of them get, I don't want to say they're tricky, they're just, you have to think about it. We're going into not just making graphs, which is procedural, but now you have to interpret the graph, which is a higher level learning. Okay, so it could be a little trickier. I mean, it's not that much different, but again, let's do domain and range. Somebody want to take a stab at domain? So these are all the x values. So just go to your leftmost extreme x value. That's it, right? Good. How about range? This is the trickier-ish one. If the trickier-ish, I don't even know if trickier-ish is the word. It's probably not because I can't even say it. But it's the trickier one. What do you think? What's the lowest y value that is on the graph? I just want to pick on something else. Anyone else have their hand up over there? What's the lowest y value? Come on, somebody help me out. Yeah.
Would it be -2? Or -1 or
Positive 1. Now the question is it a bracket or in a parenthesis? So you're thinking that because you have the open circle, right? But isn't 1 defined at -1? Like if x is -1, don't I have a y that's equal to 1? All right, so if you have just at least one output, okay, that's 1 in this case, it has to be a part of it. So this would actually be a bracket. It's because that line's horizontal. That was the trickier part. Now, what does it go up to? Well, it goes up to 3, and that's also a bracket. So you could have crazy things where there's parentheses, there's brackets, there's open circles, but you might not use a bracket. You really have to analyze what's going on, okay? One more. This is a good one too. And you'll get more practice with these in the homework. So we want domain, and we want range. So when you're talking domain, you always want to start all the way to the left on the negative x-axis. So clearly, what's the last value, right? Isn't it negative infinity, right? Because this part right here indicates that I keep going to the left without stopping. So I know the domain is going to start at negative infinity. All right, what does it go up to next that we have to sort of remove from the range? Would you think -1 is in the range? So right here, what's the output of -1? Isn't it that open circle, right? So we go from negative infinity to 1, but we're having a parenthesis because we don't include 1. And now because it's sort of split like this, I have to do, remember that union symbol, right? Which means we're just going to add these two intervals. What's the next x value where we have data for the graph? Is it at +1? Does everyone see that? So we have, and is, oh, well, not parenthesis, right? That's a solid point. So it's bracket 1, comma, and we go up to 3, but again, there's an open circle at 3, so we have parenthesis. So there's the domain. All right, now you move on to the range. All right, the lowest part of the graph is an open circle at -1. Well, all right, so we're going to have a parenthesis -1. And what do you think here? So we're good. We go up to, we're going through 0. We're good. We go up to 1. We're good. And it doesn't look like it goes all the way to infinity. It's pretty good, right? Now, what about this open circle here? Because this is an interesting thing. Let me get a different color to show you this. Because this could happen. Right, you see that? It looks like at y = 2, we have an open circle, but then we do have a point right here, right? So as long as one of them is a point, you can include that value in the range. So I'm going to change this to red. So it's -1 to positive infinity, because all those numbers are in the set of outputs to that function. Okay. All right, so if you have the graph, domain and range are both easy to find. Now, for equations, I'm only interested in you knowing how to determine the domain. So let's go over a couple. So let's say we have, you could use y, but again, you have to put it in function notation where it's y of x. Y of x equals x² - 2. So we want to know the range, the domain. Right? So can I plug in all x values and then I'll actually get a result? Is there any way to get an imaginary solution here? Or an undefined solution? No, right? So the domain here is negative infinity to positive infinity. All right, so they're pretty easy. Because remember, the only things we're looking for, undefined outputs and imaginary outputs. We need all those outputs to be real. So I hope that makes sense. Now, next one. Here we have h of x equals 1 over x² - 9. All right, so we have a rational expression. So when you had a rational expression, what did you have to look for in order to determine the domain? What was something you had to do? You had to determine the x values in the denominator that made it undefined, okay? So in order to do that, I have to take the denominator and set it equal to 0, right? That's the equation that will let us know which x values make the denominator in this equation 0, which makes the function undefined. So you solve it. So you have x² equals 9, right? And then x has to be ± 3. right? So we cannot include plus and minus 3 into our domain. So the domain is going to look kind of messy, right? Anything else works but those two numbers. So we're starting at negative infinity, going up to negative 3, but we're not including it. And we're going to union that with negative 3, comma, positive 3. Union that with 3, comma, positive infinity. So that's how we will basically negate those two numbers. That's the domain. Okay? Another one. How about f of x equals the square root of x minus 3 over 2. Okay? First off, do we have to worry about the 2 in the denominator here? We don't, right? Because that's not going to, it's never going to be 0, so we don't have to worry about it. We really just have to worry about that square root. So we know the thing inside the square root has to be greater than or equal to 0. So that means the domain in inequality form would be x is greater than or equal to 3. So that would be bracket 3 all the way up to positive infinity. All right, one last example. This one's a little tricky. I'm going to say g of x. Again, it's one more step you're doing here thinking about how these work. What if I reversed it? What if I said 2 over the square root of x minus 3, but I put that in the denominator? Okay? So again, I don't worry about the 2 up top. Leave that alone. That doesn't matter. We're going to worry about the square root. So prior to the previous problem, we said, okay, well, the radicand, the x minus 3, that has to be greater than or equal to 0. Okay? But here's where you have to change this a little bit. Do we want it to be greater than or equal to 0? Because isn't 0 in the denominator undefined? Like if I plugged in a 3 here, what would I get in the denominator? If I plugged in a 3 into the denominator. Anybody? Yeah, so you can't have that. So instead of greater than or equal to 0, we just say greater than 0. So we have x is greater than 3 in this case, simply because that radical is in the denominator. So now the domain is parenthesis 3, comma, positive infinity. With, I don't know why I used the square brackets there for the infinity, sorry. Okay. So just to review this section, really it was, okay, I gave you the definitions here of function, and we're talking now when using the words to describe them, independent variable versus dependent variable, input, output, plugging in an input to a function to get its result, which results in an ordered pair, define the domain and range, and we were able to find domain and range if we had the graph of the function, and then just determining domains from equations. And again, the only things you have to worry about are rational expressions, because the denominator can't be 0, and radicals, because they can't be, you can have a negative number in there because that'll be an imaginary output, which we can't have for functions. All right, that's everything. The homework here isn't too complicated, so we're going to have, this is going to be, I have the page number somewhere, 2.4. All right, we're going to do, so this is end of section 2.4. This is pages, I have 229, 230, 231. There's a lot of pages because there's graphs. All right, we're going to do 29 to 33. We have, why did I flip that page? 37 to 43. and then 63 to 69. And again, it's just going over the exact same example types, just giving you some homework. And again, these are all odd. Okay, so for next Tuesday, right? You've had a homework section on 2.3, and then now this homework section on 2.4. Tuesday, you're going to put in the Dropbox both of those sections, and again, it'll be a +4 because it's 2 sections worth. Does that make sense? So again, these homeworks are only helping you because you're just jacking up the exam grades, right? So if you just hand in the 2 sections and they're mostly there, you get 4 points. Only you get the negative points when you just don't hand things in. So you're handing in 2.3 homework and 2.4 homework into a Dropbox that I'll create on, I'll do it today. Okay? All right, I'm going to stop the recording.